you all understand the idea of the deformations, right? Like elastic deformation and how we can resolve that. Suppose this one. Okay, so if you're able to get back to the elastic deformations now, you can see that the we can find a cluster of local matches, and then we can eliminate all the false matches, and then we have a slightly more better approach. And here you can see how it is translated, right? Although it's not 100% correct, you can still see that the information that you're losing here is now much better in this case. Okay, so it's important that you take into account these kind of transformations whenever you're doing the global comparison. And then at the Manusia level, what happens also is that everything that was displaced much different here. See that the point XXX is quite far. In the case of the corrected version, see that at least two of them are right. So we will have some amount of false matches, but at least the amount of false matches that we have are reduced. Okay, um, and then for those of you who are looking at using the deep learning systems, there has been a number of recent books that are looking at this aspect. And the idea here is that you're not looking at the very local features, but you're looking at the global. For that image to image comparison, we are looking at. And as soon as we are doing this image to image comparison, so one of the key things is that the relative registration is much easier. Just typically, okay, you look at certain aspects of the image and then you try to associate the other, and then you're trying. Another advantage of this shape comparison is that in the previous case, you remember I told you about the minutia, where it could be 100 minutia in one image, and in the other image, it could be only 30 minutia, right? So we do not have fixed length. So there is no guarantee that I will always get the same amount of minutia. But as soon as I go to the shape-based matching, since it's taking the whole image, I'm always guaranteed to get a fixed length. Right? Any deep learning network, if I pass that information through, I'll get a quite well dimension. Now, if all the features are equally important, it's a different picture. That's a different topic by itself. But you at least are guaranteed to get this fixed length feature vector. And the moment I have fixed length feature vector, a lot of things become easy. For instance, your indexing, right? If you want to search through millions of images, you will have a fixed length vector, and matching fixed length vector to each of them is much easier than comparing it, right? Okay. And then you can also have this kind of statistical shape modeling based on intra-class, inter-class, looking at how many of the classes are very similar. And one of the ideas could be Henry's classes that we had seen in the first place. Saw the right pole, left pole. So if I know that if it's a left pole, I don't have to go check the right pole, right? So then you can cascade all these. Okay, good. And then coming back to the aspect that we had yesterday, we discussed very little about this Gabor filtering or the Gaussian blurring. And similar to Gaussian blurring, we have this Gabor filters, and Gabor filters are something like this, right? So a filter is made up of responses like this, like this. You see that 1, 2, 3, 4, 5, 5 different length, and it can be configured. So you can say, okay, how many ever filters that you want, and if I take this filter and if I move it across the image here, I'm going to get some response. And the response maps are the ones that you're seeing here. So if I'm passing that image, I see that there is a high response here. And if I'm passing the image at in second filter, I might get response here, here, and right? So what can this be used for? Um, Now there is not too many works that has been done on this. The Gabor filtering is used extensively, but the idea of these filters with the attention has not my, my so that's another area that you can explore for my signal. What is Gabor filter? What it does is that it looks in a Gabor filter you have the directions, which means that it's a frequency based filter. So then you get magnitude and you get the direction, okay? The frequency and the magnitude. And as soon as I get the magnitude and the phase, then I can create this kind of orientation. You see, it kind of tells you where the direction is, what is the direction of that figure. No, it doesn't amplify them. It extracts it, right? Because you are doing it in different orientation and different configurations, you get different features, right? So if you look at this one here, it's high energy in this area, and then slightly high energy in this area for another feature, for another filter, and the filter is staying. This is the high energy area for another configuration. And again, one more configuration, right? It kind of extracts this complementary from each different configuration. Right? Does it give an idea? Yeah. So it's nothing but you're extracting the information at different scales and phases, right? And this Gabor filtering is also very well used also in iris recognition. In the iris recognition, it's extracting the bit information. To extract that bit information, what we do is we run it through the Gabor filters, and then all the response pumps that you're getting here, and this is very vague, right? We do not see any information. So what you do is you quantize that in the case of iris. And once you quantize that, you can encode 4 bits into one single. It's one or zero. Okay? And it's the same idea that you can use in this Gabor. Okay, now as soon as I'm going from this kind of 4 filters, now what I can do is like I can think of using some features, some classifiers such as likelihood. How like from the same person, giving given that I have two responses, right? Then we are talking about not absolute numbers, but we are talking about relative numbers, right? So we are looking at the likelihood of one image being the same image given the response. All right, and then a lot of problems cannot be solved very quickly. So what people do is also they do multi-instance, which means they're not just basing upon one fingerprint, but they're basing upon multiple. So in your Aadhaar card, if you remember, you registered all of it, right? And if you're crossing the immigration point, they will capture it so that they can match one of them. And then the other approach is also to use multimodal. Sometimes your fingerprint is not only the method that gives very high accuracy. So what you can do is you can combine them with the features from face or from iris as this multimodal, right? And then you can also have multi-algorithm. What do we mean by multi-algorithmic approach? I can extract minutia field using the classical approaches, and then I can extract the orientation field using the Gabor. So now I can combine both, right? So as soon as I start combining them, now I can see that, okay, the threshold for minutia-based approach is somewhere here, and the shape-based approach is somewhere here. Now I can have a better decision system, which tells that if it crosses both the threshold, only then I say that it's the same. Make sense? Okay, good. Now we can go towards the threats because this course is also about the threats. And in the threats, one of the things that we can think about is the very primitive attack, right? So this primitive attack is you go to a restaurant, you go to a coffee shop, you buy coffee for yourself, and then on the cup of the coffee you get. And as difficult as it might sound, this lifting up that finger is quite. So here it's extremely dirty, but you see multiple here. And all you need to do is to buy this kind of charcoal powder to get, make it yourself. Also the talcum powders that is here, right? Just dust it on that and then brush it softly, and then you can lift the fingerprint. And once you are lifted fingerprint, all you need to do is to go create this kind of dummy using uh, glue and jelly, the common thing that you use for making cake, baking powder and stuff. I don't know the exact composition, but it's extremely easy to create. And then once you do that, so all you need to do is you need to paste it on your finger, right? So once you paste it on your fingerprint, you can get access to any of the systems that use it. So that means what do we need? We need to have a attack detection mechanism. So I need to be able to establish if it is actually coming from a live person or if it's coming from a pig. So this is the most interesting challenge. People have been trying to solve this problem because many cases people have been solving the accuracy, and now the accuracy has reached very good performance. So you do not really need too much of investment for that. So what people are looking at is looking at CNN-based approaches that we use for face recognition. And now CNN can be very extract the local features, right? Only takes the small amount of information and then does the convolution. And then what you can do is that instead of that, you can use the global relationship, which is commonly used, obtained using transformers. Just a quick introduction. I'll not spend too much time on the transformers. For the transformers, what comes is that it's efficient in terms of data. You do not need massive amount of data to train the transformer. You can use one of the transformers and just fine tune it like you do for CNNs. And for every single image that you have, you typically extract this small set of patches. And every patch is treated independently. And now that there is a relationship between the patch, you see that there is a relationship between 1 and 2, 2 and 3, and so on. And you can also explicitly enforce attention. Oh, right? So if you look at the performance on the top here, you can see that whatever the CNN achieves, the CNN achieves an accuracy, efficient achieves an accuracy of 85% approximately, while your DIT with a similar amount of configuration achieves very similar performance out there. Right? Now you might question here, okay, the number of images are very similar, the accuracy is quite good, but even with the given set of images, your accuracy of efficient transformers, the transformer itself is very good for every single one. So there is a very nice paper that was written in 2017, I think. And the idea is very simple, right? You have the attention that is involved in this. And when the attention is involved, you are telling that which areas of the image. Then that would mean, okay, and then the additional advantage is also that it can be as small as a distilled model. You learn and train a big model, and then you take knowledge that is only necessary sub-model, and then you sub-model so that you have a compact. And if you look at the configuration here, you can see that, well, more or less everything remains the same. And the idea here is that your parameter size is approximately, parameter size. The number of patches are very consistent, and you have the size that is much smaller for the distilled versions of the same efficient. Okay, and then now for the rest of the talk, what we'll do is that we will try to understand what is the fingerprint presentation attacks, what is it all about, and what is the strengths and limitations of this one, and then can we generalize it for unknown attacks? Because today we know that there are 6, 7 kind of attacks. Maybe tomorrow there might be one more smart guy who will come up with another kind of attack, right? So we should be able to even address those kind of. So let's start with this, and then I'll also discuss a bit on this open set versus closed set. Closed set is typically when you have the information that you know, the training data set, you know that, and then open set is the testing data set, which is completely different, and I have no information, right? So here you see that there is a very nice data set. This is publicly available for those of you who are interested in working on this aspect. So the idea here is that every year they release a data set, which is 2019, 2020, and so on. It's called LiveDeck. And the live data has number of samples. On the top, you see the real samples that is captured from the actual people. And the second one is all the artifact, which is captured from fake fingerprints. And now in the fake fingerprints, you see it can be created using different kind of approaches. For instance, using latex, which is the rubber material. And then you have the liquid ecoflex, which is another kind of material. And then you have a mix of two different and then you get a different kind of so here in the rest of the part of the talk, we will focus on these three different data sets. And here you also see that it's two different kind of sensors. One is the thermal one, the capacity one that we spoke about, and the other two are optical sensors. And the data that you're seeing here will vary across different sessions. So this is some information about the data set, which is what is important here is that you have multiple kind of training data set and the testing data set is very different. Right? You have live actual images, and then you have blue and then ecoflex and body double and latex and gelatin. But in the second one, it's a mix of those. Right? So it's a new kind of attack. Okay, so just to give a quick idea about what is happening in the field. So those of you who are interested in looking at the convolution neural networks, you can either train it from scratch or you can do a transfer learning, right? So you all know about transfer learning, right? So you train it on some known data sets and then you just simply take it and fine tune it for your own. So if you look at that, you can transfer learn it from existing mechanisms, and you see that the mechanisms here, all the different architectures, they have very good error rate. They are approximately 15% without even touching any. Right? I'm just fine tuning it, and then what I can do is like I can also say that okay, well I might not need all these features. I'll freeze some of the layers, and then retrain it using different activation functions. When I retrain it with different activation functions, you see that the error rates typically drop. Right? So the idea here is that now the networks are more tuned to know the data that we're getting. Okay? So even the highest error rate that we had here was for Inception ResNet V2. It was around 35% error rate, and then we are able to detect with less than 5%. Right? So here the performance is nothing but how well I'm able to detect fakes versus how well I'm able to detect the live. Okay? This is not matching or this is not recognition. This is only classifying they are live or if they are unbiased. Okay? Okay, so now what happens in 2015, these were the numbers, the data set from 2015 version. And then 29 version, if you look at the same thing, now you see that the error rates slightly increase. And then you can also see that the error rates decrease when you train it again from scratch. Okay? But what has changed in the last case? In the last case, the 2015, the data set was easier. Now in 2019, the data set became more complex. So the more complex the data set became, the same architectures start failing. Right? So what this tells is that you also need to consider how to upgrade your architectures, not necessarily architectures or better mechanisms to detect the attacks, because the attacks are becoming better and better. Okay, just to go back and then say, okay, should we just ignore all the convolution neural networks and go straight into the transformers? Not necessarily. You can see that just by combining top 5 networks, I can get very good result. So if I'm combining all the decision, if 25 of you, out of 25 of you, 5 of you tell that this is fake, rest of the 20 people tell that no, this is live, then I can tell that this is live, right? So I can simply do a comparison of majority. So by doing that, I see that there is a decrease in the error. So 15% equal error rate has now gone to 6%. Right? Just for the time being, just ignore these numbers. These numbers are nothing but a fixed threshold numbers, which you will learn later on. If you just focus on that one number, now you can also say that, well, I don't have time to go ask all the 25 people. I'll only ask top 5 people in the class, then get an accuracy of 6. Right? So it is decreasing by at least. So which tells there is still some possibility of using the existing architectures for your own. Okay, now why should we consider also the DEI, so the data efficient transfer? So instead of looking at all those 25 architectures and then trying to pick the best of them, I can go straight away to the efficient transformers, and I see that the error rates are much lower. So the error rate of 6.3% there dropped down to 6.8%, and then it becomes even better when I increase the size of the patch, which is 380. Right? This is the smallest configuration. This is the biggest configuration. The biggest configuration gives me around 4.7. Now here is a place where you can make a choice, telling that do I want to have a very huge network or can I have a smaller network that can be full. Okay, how does this perform? I think you have seen this network today, seen these graphs today, the DET graphs, yeah? So you understand them, right? So now you see that if I'm going to fuse all the information, then it's here. But if I'm just fusing the top 5, it's in the violet line. And then if I'm just taking the top network, the ResNet 50, it's the error rate. So here the goal is that the line should be as close to the 0 as possible. Okay, now you see that, okay, 2015 was there, 2019 was there. Now, even in the 2019, you see that the error rate is quite high. The error rate is quite high in both cases. Why do we say that? We also see that there is a gap here, right? See this gap? Which means no matter what I do, I cannot achieve an error rate less than 20, right? But in this case, it's slightly better, right? It's converging towards the 0, right? So these are the two aspects that you look at when you're looking at the D. Okay, and then comes the next part, right? So if I'm telling you that, well, the fingerprint that you presented me was not good enough, I reject it as a fake fingerprint, then you'll not be very happy if you're presenting it by yourself, right? So I should be able to explain why I think it's bad. Why should you give me a new fingerprint? And now for this case, we used what is known as class activation map, which technically goes into the layers and then try to say which of the area of the image was used for making the decision. In this case, the way to interpret this information is that the more red it is, the more useful that information is for the network. Right? So now here, in this case, if I'm retraining the network, you see that the network is actually looking at this area and trying to tell me that, okay, I think this is bona fide. This is the real image because of this information. And it's also quite good at telling that this is this is fake image because I see some distortions here, which is also understandable by you, right? Okay. So just zoom it out, and then you can also see that by forcing the network to learn the features that are very specific to that fake fingerprints, I'm able to show that, okay, I'm not only giving a decision, but I'm also able to tell why this is fake. Okay, and then you also see some kind of variations here. For instance, if you see the variation between different kind of activation functions that use the network, you see that the area that is focused in the second part is slightly lower than the area that you see in the second part, right? For the same image here, this here, the decision is made because of this area, but in this case, the decision is made because of this. So this is another problem that is very open. So if you are interested in looking at the explainability, this is a very open problem. It's a new and upcoming field. So there is a lot of scope to work on this. Okay, now if you do, now you can also question me there, right? You can also question me that while you are seeing this information here, why is the network not actually capturing the information here, which is very bad, right? So this is a very valid question. If you ask me, then what we can do is that we can try to see what happens in the case of the efficient net. And in the case of the efficient net, it is telling me that those are the areas it is looking at while it's saying that it is bona fide or if it is fake. And you see a clear difference. But although you see a clear difference, also make sure that this is not really looking at the information information that we need to, right? So the idea here is it is a visualization tool. It's helping us, but it's not solving. Okay, so that gives an idea for you to work in future. And then comes the second part, right? So today morning there was a question: why should I train on one network and test? Why should I train on one data set and test on different data sets? So this is a typical case. So you have the training done on one kind of data set, and then you are testing on the same sensor, but the material is changed. So the content used for creating the fake fingerprint is now different. As soon as you have a different content that is used for creating the fake fingerprint, you see the error rates kind of go out. So the 10% that was there up, that was the error I was getting before. Now, just by changing the material, the error rate increases to 25 or 18% approximately. Right? So this is the reason why you need to look at the solution and try to generalize across different kind of materials. And again, the other idea is that although I said efficient transformers are good at this, even there you can see that the error rate is right. You see that in the previous case the error rate was less than 5%, and in the next case you see that the error rate is approximately 5%. Right? So generalization is still an open problem. And what you can do is you can try to come up with some strategies to merge all of them. Um, and then is the device interoperability. What is device interoperability? Today I might be using a sensor from company A, and tomorrow the company might go bankrupt, and I'm forced to buy sensor from company B. So as soon as I buy it from company B, you see that the error rates shoot up. So the error rates are 46%, and in the case of the fusion, it's still 26%, which means 26% of the time I'm not able to detect somebody who's trying, right? So which is not good. So what do we do? What we can do is we can look at the other approach. I don't know if you remember, but when I started the lecture today, I said that it was the fingerprints were very incorrect. It's the same fingerprint that you find beneath the skin, and they go all the way down, right? So if I'm able to tap into that information, then I'm able to say that, okay, this is a real fingerprint, or if it's a fake, especially if I'm putting a fingerprint on the top of it, right? So here's an idea of optical coherence tomography. This is commonly used in the medical field for, especially for when the uh, when the babies, when there is a pregnancy, they do this kind of tomography where they try to figure out what is happening beneath the skin surface, right? Which is exactly the same technology here. So here you have the finger is put here, and then there is the reflector here, and the light is the LED is flashing light from there. So you have the light from this side and the reflector from this side, and this passes through a number of layers, right? So because it passes through a number of layers, what you are seeing here is that you are seeing the uh, the epidermis, which is on the top of the fingerprint, and then beneath the fingerprint, if you follow the same line, you see that there is also this dermis, which is the second finger. So if, for instance, if I have extra layer on top of my fingerprint, the information that you get here will be very different from the information that you get. Make sense? Inherently. This was a work that was done by our partners in France in a project. And how does the fingerprint actually look like beneath the skin or once you extract it? So you see on the top one, it's a layer number one of the fingerprint. And then two is the layer number two, and then layer three, layer four, layer five, and so on. So as the light kind of diminishes hitting the surface of the internally, you see that it's only few areas that are selected. Okay, but the interesting idea here is that since if I'm going to have a fake fingerprint on top of my finger, this information and this information will be very different. Okay, so that makes it inherently stronger for that access. And then you have also the second part, right? The second part is looking at the, if you pay very close attention, now you are able to also detect the sweat codes. You see that small white dots that is available? So these are the sweat codes, right? So by increasing the capability of the sensor, you are able to get the high quality fingerprint, which is also attack. Mhm. Mhm. Yeah. Yes, that is a very interesting question. So the question was, what happens if I use 6 layers of my fake fingerprint on top? It's a very valid question. So what you need to do is that if you want to increase the capability of that, then you increase this one, right? So this camera configuration you can change, which is, by the way, this is still a very costly technique. It's quite bulky. The sensor is approximately of this size, so it has not become very compact so that we can use it here. So, but people are working on making people from physics and optics background. They are looking. Okay, but it can fail. So the point here is that none of the mechanisms that we are developing will be 100% fail. Everything will have some link. Okay, and then just to show how the fingerprint quality also matters is that if you take those two fingers, you see that the amount of information that you're getting will vary across the. Now, here is a good opportunity for you to reflect on the information, right? For instance, the information that you're getting here, this one is not available here, right? So what can I do? I can merge the information from this, and then I have a better representation of the whole thing. So this means it's not only attack resistance, but it's also good for identification. While I say that it's good for identification recognition performance, you should also think that the classical databases that we have as of today, they are all optical, right? Or capacitive. So I should be able to match these fingerprints with classical. So there is another paper which is related to this, where you can see how the matching is. But you get the idea. So there is this device interoperability and the information. Okay. Okay, just to conclude on this, so one of the directions that you can look into is the transformers for improving the performance. Um, but then also imagine the scenario or think about the scenario where I showed that although it is very good, still not able to scale up for open set. So open set problems is still an open issue. That is another problem. And the other aspect is that the explainability of these networks is still very primitive. It's not really solving the problem, but it's helping us to understand what's happening. Okay, so that concludes the part of the talk. So what we can do now is that we can try to understand the fingerprint code. If you have your code ready. So everybody got access to the data set? Yeah, and the EXEs. So for those of you who are using the Windows, you have to put the EXE into that folder, the same folder. For those of you using Windows or sorry, Linux or Mac, you can just get the folder as it is, and it should be able. So EXE is on the in the additional folder on the Google Drive. So if you go to day one, no, in the day one, biometric authentication. Yeah, biometric authentication system. In that you have fingerprint authentication, and in that you have the EXEs. Yeah, so there are two files. One is Bozort and one is MinDTCT. So what we do here is that in this case, we are extracting the minutia template using one software, which is called MinDTCT. And then we are comparing them using another one, which is called Bozor, right? And then remember to configure this to the right folder path and try to give the file path for the images. And the second one is the path where you want to store the minutia files. So once you have configured them, and then it runs through the entire loop, and then try to find the path. And then what we're doing is that we're calling uh, the Windows executable or the executable itself, and then asking it to return the minutia. Okay. So this is the place where we're calling the exe, and in this case, you would want to give the right path for your Windows exe file, and then call this same command. So comment out the line. This one, this one is for Linux and Linux and Mac, and the other ones are for just for the Windows systems. If your process succeeds, then you should be able to get the XYT files, which are typically the files for X, Y, and the minutia. So you're able to run that. Yeah, I think you could also use the collab. For those of you that are happy about collab, just import it as a collab file and then configure the right paths, and then you can just run it from there. It doesn't have the exe in the. It has in the min DTCT. Yeah, you have to copy those files into this folder where you have the IPY and B, because sometimes the Windows gets cranky about not finding the right path. So its easiest way is to just copy those files in the same folder. And when you run this one, it's going to generate a bunch of other files such as BAW, DM, HCM, LCM, and all, which are not relevant. So we can just simply delete them, and that's what is happening in this part of the code. It should be in the Windows. Yes, those are the ones. I mean, the extension are hidden. Yeah, just copy. So, and then since we are talking about the generative attacks on the fingerprints, what I'll also do is I'm going to release one more bunch of code which is based on generative adversarial network, and this code will help you to create fake fingerprint samples without any real data. Okay, and then you can also use that one to see how many of those samples are misclassified. That we will take in the next part. Okay, so if you have uh, if you have been successful in extracting the minutia file, just out of curiosity, you can go and look into the minutia file what it consists of. Let's go here. You see this one? You see the minutia files? So this is a typical minutia file. It tells that at the location x comma y, which is which is 115 and 11, the orientation is 0 degrees, and the type of the feature that is found is like this, right? So it puts all those information. Now, if you scroll through this, you see that it's around one or 154 minutiae as found. But if I simply take the next one, now it has become 140. So you see the problem that I discussed in in the first part. I said the number of minutiae that you are going to get is not always the same. So then you need to have a comparison. So now you can start doing the comparison using the second part. In the second part, now we use okay. So in the second part, you can simply if you want to see how the minutia actually look like, you can just run this one. Okay. Change the path. But rerun this. So you see, it's not really a complicated process. It runs quite fast. So even if I restart it, it's in less than a couple of minutes. It will be completed. Now you are seeing that it's already at 50%. Okay, and then I'm randomly taking an image. And then I'm trying to overlap the minutia files on that. See that here now? It's a visualization where I'm just introducing first, this is the actual fingerprint that I've read. And this is a latent fingerprint, right? Because it's a latent fingerprint, you also see some kind of annotations here. And then you have the minutia point. Now, can you see that there is a spurious minutia here? Red dot, red dot, red dot here. These are not related to the information at all, right? So we need to be able to match it. So to match that one, what I am doing here is that now I call another function, which is called bozor3. For people who are using Windows, you have to just comment this line and uncomment this line. So this should be uncommented. Okay. Once you do that, you get the matching between the two files using the X, Y, and T, and then you get a result out of this. Okay. Now you can see that it's crossing already 7%, 13%. So it's completed now. Okay, I know that it's a lot of information that I'm giving. I don't expect you to understand every single thing, but at least I want you to go back home with the information that you have, and then try to reflect on it, and then try to read a bit more. Run this code, and then once you are comfortable with this, what I'll do is today I'll release another set of code, which is for generating the synthetic samples. And now you can try to use the real samples versus synthetic samples, and then try to see how many of them actually match against each. Okay, and the just to wind up and connect everything that you guys did with the first part, I can go back to this histogram visualization of the scores, and that tells you that how many of the scores were uh, matching. So a good number of fingerprints were got 200, and some of them got very low score. And then if you now look into the DET, no, forget about this block. This block is not good. Just run the second block. Now you can see that the equilibrium rate of that system is quite low. It's around 0.07 or less than that. Then you have second one. Then you have the DET score, which kind of gives you the aspects that Professor Khanna discussed today in the morning. Huh? It varies. How much is it? Yeah, it's the same. For this one, which one is the one that you're using? And can you scroll next? Next. This one? How is that one? Oh, that is the okay. That's the ROC curve. Let me also show the ROC curve. Oh, you have the ROC. Praveen, did you say something? We could not hear you well. So that might be slight variation because of some samples. Okay. Any questions on the aspects that we have discussed so far? But you might see a small variation in the DT, but it's not very too much. Okay. Any questions so far?